Hello students, I am Sanap from Department of Physics, RBNB College, Shirampur. This is my lecture number 6 on the topic Electrostatics of the subject Physics for 11th Science. In previous lecture, we saw about the electric lines of force. What is meant by electric lines of force and what are their characteristics. An imaginary path traced by positive charge is called electric lines of force, and also we saw about that some characteristics of lines of force. Now today we are going to next article, that is electric flux. Electric flux, which is denoted by phi E, electric flux. The number of lines of force per unit area is the electric field intensity or electric field. Now here electric field is equals to that number of lines of force, that are electric lines of force, divided by area enclosed the lines of force. Area enclosed the lines of force. This is the electric field E, and now this number of lines of force, that number of lines of force is equal to this electric field E into this area. Now this number of lines of force is equal to that electric field of that area enclosed by that lines of force, that gives the electric flux here. And now to understand this concept, what is meant by that electric flux, consider the small surface area here. This is placed in a uniform electric field. This electric field E here, which is directed like this one. And now this is the surface area. Our simplicity, we consider the small surface area here ds, and this total area is the S. Now the theta with the angle between this E and this surface S is there. Now this electric flux is the lines of force passing perpendicular to this surface area. how much lines normally passing through that surface area, means that are directed like this one, perpendicular to that one. Now this is the surface and that electric field will be there, and now this E with the electric field intensity, and now what is this lines of force are perpendicular to that surface area. And now our simplicity consider here the small surface area ds, and then due to that surface area d phi, that is the electric flux for that surface area will be that E into that surface ds cos theta, E into ds cos theta, and now that can be written in a vector form E bar dot ds bar. This is the d phi. This is a equation 1. This is a small electric flux on that surface area ds. Here surface is again that area is again a vector quantity, and this E be the here vector quantity, but this electric flux is a scalar quantity. And now here what is the total electric flux due to that surface S, we can obtain by taking this integration of equation 1, and therefore total electric flux, total electric flux obtained by integrating equation 1 we get. And now we integrate that equation 1 here, the total electric flux due to that electric field phi E is equal to integration of this d phi, and now is equal to integration of phi is that E dot here ds bar, or is equal to into that E into that integration of ds here, and now is equal to this E dot ds into that phi E, that is a total electric flux is equal to E dot E bar dot S bar. This is a scalar product. Here integration of this ds bar is the total surface area, this S bar here. And now in this way we can obtain the total electric flux due to this total surface here. S with the total surface, our simplicity we consider the total surface area S here. Now these lines of force or this electric field is perpendicular to this surface area ds, and theta be the angle between that E and that surface area here ds. Now here theta be angle between that E and ds. And now here we consider that surface area ds is resolved into two components, that is ds cos theta and ds sin theta. Now here we consider that component ds cos theta here, and now therefore this electric flux for the surface ds will be d phi is equal to E ds cos theta, by the definition of that scalar product, get the E dot ds. This is the d phi, and now integrating this one, we get the total electric flux of this surface ds. Okay, this is about the electric flux. And now we say the next article concerned with the topic is the Gauss Law or Gauss Theorem in electrostatics, that we have to study now. Gauss Law in electrostatics, that scientist in 1707 to that 1855, that obtain the mathematical relationship between electric field E and charge Q. That is a mathematical relationship between electric field and electric charge will be introduced by this scientist Gauss, which is known as Gauss Law or Gauss Theorem in electrostatics. See the statement of this Gauss Law. The total electric flux enclosed by any surface area is equals to that 1 upon epsilon 0 times charge enclosed in it, that surface. This is the statement of this Gauss law. Now mathematically this total electric flux phi E is equal to that suppose charge is plus Q divided by epsilon 0. That is 1 upon epsilon 0 times that charge is the electric flux. Now phi E is equal to that plus Q upon epsilon 0. Means we explain that suppose this consider here a surface area of any shape here. Suppose that there is a charge is Q1 in that enclosed surface. At that time that electric flux is equal to that charge, this plus Q divided by epsilon 0. Here charge is the Q1. If charge is there Q2, then phi E is equal to Q2 divided by epsilon 0. Here epsilon 0 the permittivity of free space or a vacuum. In this way, for that charge, generally we write that electric flux phi E is equal to plus Q divided by epsilon 0. And now we have to prove this theorem. That is the Gauss law in electrostatics here. Okay. Now see the proof of that Gauss theorem. Mathematically, statement is phi E is equal to that Q upon epsilon 0, and now here we see the proof of this Gauss's theorem. Now consider here the enclosure surface of any shape, and now inside it there is the electric field this is the small surface area ds, and now here here is the electric field E, and this angle is a theta, and that is the component will be there of that surface area ds, and theta with that angle between E and ds. Now here this charge plus Q is situated at this point O, and which is at a distance R. This surface area ds is separated at distance R from a point O here. And now in previous lecture we obtained that expression for electric field intensity at a point due to a charge E is given by 1 upon 4 pi epsilon 0 Q divided by R square. This is the electric field intensity due to a point charge at a point here. This is a point or simplicity. We consider the point P here. This is a point P. Now at point P, electric field due to charge Q is given by E is equal to 1 upon 4 pi epsilon 0 Q upon R square. Already we obtained this equation, and now write the explanation of that figure. Here consider plus Q charge is situated at a point O in enclosed surface of any shape. Let P be point of small area ds, which is at distance R from a charge Q here. And we know that the electric field intensity E at point P is given by that E is equal to 1 upon 4 pi epsilon 0 that Q upon R square, the equation 1 here. Now this equation already we obtained there. The direction of E is away from point O. This direction of E is away from this point O, and theta with the angle subtended. This here theta be angle subtended by area ds at point O, or that angle between that E and ds, this area ds makes an angle theta with the direction of electric field E here, and therefore already we saw about that what is the magnetic flux. The small magnetic flux on area ds is that d phi is equals to d phi is equal to, already we obtained that E ds cos theta. This is equation 2. This is electric flux. Already we obtained for this surface area ds here. Now put the value of E here, that is 1 upon 4 pi epsilon 0 Q upon R square into that ds into this cos theta. Now that ds cos theta divided by R square, modify that one, 4 pi epsilon 0 here, Q upon that one into this ds cos theta divided by R square. This term we write in this manner. This is a small electric flux d phi is equal to Q upon 4 pi epsilon 0 ds cos theta upon R square. Now is equal to that Q upon 4 pi epsilon 0 into this d omega. This is a d phi. Here this d omega is a that solid angle subtended by area ds. Solid angle subtended by ds at point O. At point O here is the solid angle here, and now therefore d phi is equal to Q upon 4 pi d omega. This is equation number 3. Now up to here we obtain this electric flux on that area ds. We have to find a total electric flux by this total enclosed surface area of this any shape, then total electric flux can be obtained by integrating equation 3. We get means that total electric flux phi E is equal to that integration of d phi. Now continue here this equation that phi E electric flux, total electric flux is equal to that integration of that value of d phi is q divided by 4 pi epsilon 0 into d omega. Now is equal to that q upon 4 pi epsilon 0 integration of this d omega. This is the phi E here. Okay, but this integration of this d omega is the total solid angle. Total solid angle subtended by that enclosed surface area or enclosed surface at point O, means here total surface area subtended by that enclosed surface at point O is this one, and value of this is equal to that surface area is equal to 4 pi. Total complete sphere that will be 4 pi, and now put the value of this integration of d omega is the 4 pi, that is the total total solid angle subtended by that enclosed surface, and therefore this equation becomes that electric flux, total electric flux is equal to q upon 4 pi epsilon 0 into value of that d omega is the 4 pi. Now this 4 pi get cancelled, and now that phi E is equals to that q divided by only epsilon 0 is remaining here, only epsilon 0 is there. And now if this enclosed surface consists of this only positive charge q here, and then total electric flux is the 1 upon epsilon 0 times that charge enclosure in that surface area. Now we can modify this one in a different way. Suppose that surface area consists of a charge qn, then phi E is equal to that charge qn divided by epsilon 0. This is the total electric flux of that enclosed surface of any shape. And now in this way we get the proof of Gauss's theorem in electrostatics. Okay, now in shortly I explain that first write down the statement that mathematical relation phi E is equal to Q upon epsilon 0. That is the statement of that Gauss's theorem. Now we have to prove this theorem. Consider this enclosed surface of any shape. Now this charge plus Q is situated at point here O, and now our simplicity, we consider the small infinitesimal surface area ds, which is at distance r from this charge. And now here electric field E is directed as shown in figure, and now theta with the angle between E and this small surface area ds. And now we get the we obtain that electric field at a point due to a point charge is given by E is equal to 1 upon 4 pi epsilon 0 Q upon r pi. And now we use that definition of the magnetic flux on that small area ds will be there. Now put the value of here E, then equation get like this one. Then d phi is equal to Q upon 4 pi epsilon 0 d omega here, where d omega is the solid angle subtended by that small area ds at point O here. And now we have to find what is the total electric flux that can be obtained by integrating this equation 3, and now get that phi E is equal to integration of d phi means this equation 3. Now here integrating this value, get equation in this form. Now integration of d omega is the total solid angle subtended by that enclosed surface at point O, and its value is a 4 pi for a solid angle of that enclosed surface at point O is the 4 pi. And now put this value here. Now this 4 pi get cancelled, and then answer will be phi E is equal to Q upon epsilon 0. This is the mathematical statement of Coulomb's law. Now this surface consists of a charge Qn enclosed in it, then phi E is equal to Qn divided by epsilon 0 is the another form of that Gauss's theorem in electrostatics. Okay, now we can stop here.